Hi, good morning, good afternoon, good evening, everyone. Thank you so much for joining us. I'm Stephanie Call, and I'm here to introduce my colleague, Dr. Emily Blair. She's a senior application scientist at Countable Labs. And she spent the last 3 years working with researchers like you to develop Countable PCR and to help them make the most of their assays in Countable PCR. So she's here today to share with us about using Countable PCR for rare event detection. As she's speaking, please feel free to drop questions in the Q&A box at the bottom of the screen as she's presenting. I'm going to join us back at the end to help field all of those questions. So with that, I'm going to hand things over to you, Emily.
Okay, thank you, Stephanie. So, like Stephanie said, my name is Emily, and today I'm going to be talking with you all about how countable PCR can really change the game for rare molecule detection. We have higher sensitivity, more straightforward assay design, and with less assay development as well. So, I want to start off by talking about what is the current state of rare event detection. Okay. So biology is very complex, and we as scientists, we're continuing to ask more and more challenging questions. We want to be able to detect rare signal with low input in highly variable samples. But most tools on the market were really built for more bulk averages, not for single molecules. And we really need technology that fits the biology of today and tomorrow. So in many, many conversations that I've had with different people, I've heard really the same thing over and over again. Researchers are struggling with common issues. So for example, low input samples like cfDNA, liquid biopsy, single cells, these are becoming more and more common. Rare targets are also becoming more standard. These are no longer edge cases that we're working with. And this is really critical for early detection as well as for minimal residual disease. And then thirdly, biological samples have a lot of variability. And we expect that you'll be only encountering these challenges more and more in the future. Your current tools fall short at addressing these challenges. They don't measure high and low abundance targets at the same time, which makes it very difficult to get the sensitivity and the precision that you need for reliable rare event detection. So the current tools fall short in different ways. qPCR is very fast, but it's insensitive. Digital PCR is better at sensitivity, but it has lower throughput, and it doesn't allow direct comparison of rare events alongside your common benchmarks. Next generation sequencing is very powerful, but it can be overkill when you're working with just a few targets, and it's very costly to scale. So oftentimes you're stuck trading time for resolution or cost for confidence. But countable PCR doesn't force you to compromise. It's all three: fast, precise, and scalable. Countable PCR is not another flavor of digital PCR. It's fundamentally a new approach. With this new technology, you can now count your targets directly with no Poisson correction needed, no manual thresholding either. So you can get confident results fast with less ambiguity, higher sensitivity, and assays that can even be developed in days instead of in weeks or even months. Here, I want to share this quote from one of our early access users that has already seen great success using Countable PCR. So she says that the Countable PCR platform is a game changer. With 30 million compartments, we're seeing significantly higher sensitivity with fewer reactions in our oncology assays, and new opportunities have opened up in the fields of NIPT and infectious disease. The workflow is easy with potential for automation, and the precision of the results is higher when compared to other commercially available platforms. And this quote is coming from our early access user, Trisha, who is a director of R&D at Labcorp. So in addition to being a game changer for generating sensitive data, with Countable PCR, you're getting single molecule data without having any extra complexity in your workflow. So how does that work? Fundamentally, Countable PCR is counting. So in this video, I'm showing this is the instrument collecting different images from the PCR tube, where each signal is a different target by channel. And you can see in this example, we used 4 channels, so 4 colors per reaction. And by using a direct counting approach, we open up lots of new avenues for getting better data for rare molecule detection. You're able to image the entire tube with up to 35 microliters of analyzable DNA, so you're never missing a rare event, and you're not losing any molecules to dead volume. Direct single molecule counting ensures precision, and since, as you saw in the video, each target really occupies a distinct spatial location within independent compartments. So your assays are very clean, and they're not having to deal with PCR bias or any type of signal interference or spectral overlap. So I've talked a little bit about how simple the PCR workflow is. So next I want to provide some details on how the workflow itself works. So to create the countable matrix, the setup is very easy and everything is done in one tube. And this really reduces the risk of contamination. So first, everything is prepared in a spin column. You can see the spin column in the bottom corner here. This is our spin column in our tube as well. So everything is prepared in this setup. This allows you to input 35 microliters or a microgram of analyzable volume, which allows you to find very rare targets. The spin column generates the countable matrix, which forms over 30 million compartments in a 50 microliter reaction volume to really ensure that there's true single molecule suspension of your targets. And it's this matrix that is really what makes the direct counting possible. Your targets are then amplified directly in the rigid 3D matrix to ensure that there's no bias and that targets are spatially distinct. And then the countable instrument images the whole tube, which maximizes analyzable volume, and it allows for statistically significant counts across a 6-log dynamic range. And here I really want to highlight that with over 30 million compartments being generated and having those targets being in physically isolated space, it's really possible to get that higher sensitivity detection in a lot fewer reactions compared to traditional PCR methods. So now that we have an idea of how this technology works and what makes countable PCR so unique, I want us to look at how it can transform rare event detection workflows. So first, countable PCR outperforms qPCR and digital PCR. qPCR lacks accuracy when it's not combined with standard curves, and this does not offer direct quantification. Digital PCR, on the other hand, is only able to account to about 200,000 targets, and this gets less reliable as your concentration gets higher. You're not able to directly compare high and low abundance targets at the same time. But with countable PCR's direct counting and 30 million compartments, you can get precise linear counting across a 6-log dynamic range, as shown here. And that dynamic range can be leveraged to do some really cool experiments for rare event detection. So countable PCR is capable of detecting 30 molecules in a million, all in the same tube. So this means you can run really high amounts of DNA to expand your search for the rarest targets without having to do any type of hyperwelling. This gives you really sensitive limit of detection without having to dilute your high abundance targets or having to run them in different reactions. Countable PCR lets you push those limits of detection with high load experiments. And in this specific example, we ran 3 micrograms of DNA and observed a very low VAF of 0.004%. This sensitivity is easy to achieve. Rather than spending a lot of time optimizing assays to push limit of detections, countable PCR lets you get started out of the box. So let's review how that's possible with a few examples. Countable PCR works differently from digital PCR because we're directly counting molecules rather than having to rely on Poisson statistics. So not only do digital PCR systems have far fewer partitions, but they are relying on each of those partitions being occupied by only one target molecule. And as your target concentration gets higher, above about 100,000 counts, the data becomes less reliable as empty partitions become too infrequent, and multiple targets are going to start occupying the same partition. When it comes to multiplexing, this becomes even more complicated. This is when you start having a lot of issues from signal interference and amplification bias, which really can help you or can really prevent the real picture from taking shape. Countable PCR ensures that only single molecules occupy each compartment because of the nature of our matrix formation and the high number of compartments that we have. This really prevents crosstalk, and it ensures that you're able to get clean signal for counting different targets. That way you can spend a lot less time optimizing multiplex experiments in particular. So as I mentioned, because of these compartments, we're able to offer a less expensive, faster to iterate technology for multiplexing, which is called universal multiplexing. We are also compatible with TACMAN multiplexing, but universal multiplexing has some unique advantages that I want to discuss today. So first, universal multiplexing from Countable Labs uses standard oligos instead of TACMAN probes for your targets. This makes it much faster and less expensive to order the materials that you need to set up multiplex experiments. Universal multiplexing is also pre-optimized for you, so you're not having to do any type of experimental work to balance your probes or your signals. Because of this, you can get multiplex assays designed and tested with easy-to-interpret results in just 3 days. So next, I want to talk a little bit about how this universal multiplexing works. It's a very straightforward technology. Universal multiplexing lets you design quantitative multiplex experiments like TACMAN, but with the same ease as if you were working with CyberGreen or EvaGreen. So how this works is you simply design a standard forward primer with a universal adapter leading on the 5' end. And we have different leader sequences for each probe channel. Next, you'll add your probe to your reaction setup. And as the amplification carries out, the probe binds with the adapter sequence and fluoresces, which gives signal in each compartment that would then correspond to a specific target. So this means that you're using this technology, you're able to get faster iteration. So oligos are able to come in 1 to 2 days instead of having to wait weeks for a TACMAN probe. And the cost of these standard oligos is closer to about $30 rather than hundreds of dollars that you might expect for a probe. People are already finding success with Countable PCR. They're not just getting answers, but they're changing their actual approach to their work. So this includes consolidating qPCR reactions, targeting long-read amplicons, getting better validation of next-generation sequencing trends with direct, low-variability counting, and then easy automated DNA linkage experiments so that you can really expand what's achievable with PCR today. So first, I want to share how we collapsed hundreds of qPCR reactions into a single countable PCR reaction. And this work is coming from a researcher that we worked with from the University of Georgia, and they were working to detect latent pathogens. So in the top panel here, multiple qPCR reactions were required to determine the presence of the pathogen. Each dot on this plot represents one sample, and for samples with higher CQ values, there's about 10 reactions represented for each sample. And you can see with the dotted line at the top here, which represents the percent positive reactions, that this is close to 100%. But when we start looking at the lower CQ values, where the target is more rare, it's a completely different story. So each of these dots is representing closer to about 100 reactions per sample. And as you can see from the dotted line, the confidence is very low for these. In the bottom panel, Countable PCR shows pathogen detection from the same set of samples as the first panel, but each bar represents just one reaction on the Countable platform. And this is all that was needed to identify the rare pathogen target for each of the samples. So you can see with this type of approach, we're able to save time and we're able to save effort with this reduction in optimization. We're even able to save cost because once you're running this many qPCR reactions, it's really not the cheaper option anymore. Next, this data set shows how you can measure large amplicons with Countable PCR. Other methods like qPCR and digital PCR can't do long amplicons because it requires a lot of amplification or it requires a lot of optimization. And the amplification doesn't take place in the isolated space, which reduces efficiency. But Countable PCR changes that. So in this experiment, we measured counts of increasing amplicon size up to about 2 kb using both TACMAN and universal multiplexing approaches. Up to 2 kb amplicons were detected by Countable PCR with minimal optimization, and the results from both TACMAN and the universal multiplexing match very closely, as you can see with the 2 bars going across. So Countable PCR really allows you to quantify the presence of whole isoforms, which adds flexibility to your assays while letting you learn even more about gene presence. Countable PCR is also powerful enough to give you statistical confidence to validate trends that were identified with next-generation sequencing. So ultra-deep read next-generation sequencing is very costly for scaling. Here, UPenn researchers performed DFEN-seq and identified a positive trend between chromosome gain and age in this panel. They then tried using digital PCR to validate their sequencing results, but digital PCR didn't have the statistical confidence because it's so error-prone. Countable PCR shows very tight reproducibility in this panel, so you can catch real, meaningful results and not just patterns. Countable PCR can be used to start getting statistical confidence right away in as few as 3 days with the universal multiplexing chemistry. The last piece of data I want to show is where we designed a linkage analysis for getting complete versus partial vector genome information for AAV. In the graphic, you can see that the color of the signal in each compartment changes based on if the vector genome is complete or not. So for example, you can see a distinct blue compartment for the partial genome that contains just the CMV enhancer, versus the compartments appear white when the genome is complete, and all 3 targets are present in a single compartment. The analysis algorithm has been rigorously tested to precisely be able to determine linkage using this principle that we can see in this image. Countable PCR makes linkage analysis easy thanks to the 30 million spatially isolated compartments. So now that you've seen some examples of how Countable PCR can be used for rare event detection, I want to review how the Countable platform can help you ditch the limitations of other PCR methods. Digital PCR is expensive. So you're having to order TaqMan probes, there's the cost of labor, the cost of the time, often lost to a lot of failed reactions, but sometimes it's really important to multiplex. So digital PCR is going to be your best option. Countable PCR with universal multiplexing brings down the cost a lot and also reduces the optimization time thanks to the easiness of using the universal multiplexing. This example specifically came from a CLIA lab collaborator, and they did a cost calculation to show that using Countable PCR, they were able to save over $10,000 a month with our platform. Countable PCR has the lowest cost per answer, while providing absolute quantification, high precision, high dynamic range, easy multiplexing, and easy, fast assay development in just 3 days with universal multiplexing. So this means that you'll be able to work faster and more efficiently, getting more answers in one tube with less optimization time so that you can really stop making trade-offs in your experimental design. Here we show that there's no crosstalk between different channels. So that means for channel 1, for example, you're only detecting signal from channel 1 and so on for the other channels. So this essentially means that you've got no crosstalk and you can avoid having to do any type of compensation experiments so that you can get clear, unambiguous results for 4-color multiplexing the very first time that you try it. In each Countable PCR run, you also get a report with built-in metrics that give you quality information about each amplification event in every tube. Validation and report of the ID score, which is shown in the top left of these histograms, provides a quantitative read on quality metrics for each of your amplification events supporting GMP. The report also outputs direct counts with automated thresholding for easy and fast data interpretation. Countable PCR sees what others miss. We capture every single molecule. That means 10 times the sensitivity and simple, clean data. Plus, you can get more done in one tube, especially by comparing both rare and frequent events in the same reaction. You can also speed up assay development without having any trade-offs. Here, I want to share 2 quotes from our early access customers to really drive home how powerful Countable PCR has been in their workflows. So first is coming from a professor at the University of Georgia, and he comments on the dynamic range of the platform that has really allowed him to do direct, precise counting of rare molecules. Secondly is a collaborator from a CTO, and he plans to replace all of their NGS work with Countable PCR. At Countable Labs, we have a whole suite of products that will get you multiplexed, high-resolution, high-sensitivity PCR results. We aren't just digital PCR in a new box. We're a fundamental change in the quantification of genetic targets. So that way you can start detecting what those other methods are missing. And on this slide, I also want to point out our assay design service here. So we offer 3 distinct tiers to really empower our customers' unique needs. These tiers range in complexity from in silico support to a full white glove service support. And this could include analytical characterization of your targets or even running some of your samples. I hope this has helped you understand what makes Countable PCR such a unique and powerful tool for genetic analysis and rare event detection. Finally, there's a tool that will help you spot 30 molecules in a million all in the same tube. So thank you so much for joining me today. Please visit our website to learn more about Countable PCR and how it can transform your workflow. You can also use the Contact Specialist section on our website to contact us with any questions or to schedule a lunch and learn for your team to learn about Countable PCR.